Okay. Okay, thank you very much.
Go ahead.
Yeah, you can hear me, yes? Everything's fine?
Yes.
Yeah, just double checking. Okay, yes, so today I'll be talking about how to overcome the kind of limitations which are often thought to be fundamental based on relative entropies through the use of so-called probabilistic protocols. And this is joint work with Ludovico Lamy and with Mark Wilde, and it is available on the archive. Okay, so let me just jump straight into it. What is happening here is that we are concerned with the transformation of some state rho into some other state omega. We want to convert one state into the other, but of course the operations that we can do are somehow constrained. So I will be referring to them as the free transformations, the ones that we are allowed to perform. And so in the kind of our favorite IID setting, we often look at what happens when we have access to more copies of states. So what this looks like is that we have some machine that prepares many copies of the given state rho. Then we plug them into some protocol, and this protocol is supposed to output states which are, let's say, approximately equal to this target state omega, and then we can impose some other conditions on this error. So the well-known kind of rate in standard quantum Shannon theory is defined as follows. It is, again, in this kind of setting, when we have many copies, we are looking at what happens in the limit of n going to infinity. So essentially, what is the largest number such that we can transform n copies of rho into Rn copies of omega, with the error in this transformation quantified by the trace norm going to 0. So this is kind of taken for granted in most applications of quantum Shannon theory, but let us look at what this actually means. So what this does is it takes into consideration the number of copies. So the only cost in this kind of framework, the only kind of thing we're paying essentially in this transformation is the number of copies. So the rate asks how many copies of rho we need to generate, such that at the end we will have desired some copies of the state omega. Now, the problem with this is that this never takes into consideration how difficult it is to actually manipulate n copies. So it allows us to generate many copies as long as we pay for this kind of cost of generating them, but then essentially it assumes that we can manipulate them for free. But I mean, obviously in practice, both of these things should be kind of costly. One should be number of copies of the given state, but also the size of the quantum memory needed to actually transform these states. And Shannon theory essentially ignores the second aspect. And of course, this is, in general, Shannon theory is like an idealization of an approximation of the practical setting. But the thing is that in most practical scenarios, generating the states is actually the easier thing to do. So we can actually create many copies of states, but actually coherently transforming many copies, that is where the difficulty lies. So in this approach, we propose to do essentially the opposite. We will ignore the number of copies needed and focus only on the size of the quantum memory which is required to transform these states into the desired output states omega. Now you might think this is just the same thing, but if you think about this carefully, what we are doing now, we are only paying for the cost of this protocol, the size of the protocol. That is the only kind of the cost function of this transformation is only the size of the protocol. So what we can do for free without any additional cost is to repeat the same protocol, because we are not paying for any number of copies. We can keep creating copies of rho for free now. Essentially, we are taking the limit as n goes to infinity anyway, so we are only concerned with what is the size of the quantum memory, or how large of a coherent transformation we have to be able to perform. But once we are able to perform it, we assume that we can repeat it. And okay, so what does this change at the level of the rates? The level of the rates, you might remember, this is the kind of definition of the usual rate. We have some channels which transform the states rho omega into, rho tensor n to omega. What we can do now is apply not just quantum channels. What we can do now is apply probabilistic protocols. So now we will assume that these are no longer CPTP maps. They no longer have to be essentially trace preserving. They can be trace non-increasing probabilistic maps. And essentially, we don't care about the actual probability of success of this protocol. because we are not paying for the number of copies of rho in this transformation. So we can just keep repeating the protocol until it succeeds. And we are only paying for the size, again, of this protocol that is required in the transformation. So this is the fundamental definition. Definition we'll be using is the probabilistic rate of rho to omega. It is defined using these operations, which are not necessarily trace preserving. We will also be looking at the strong converse rate defined in the same way. So essentially, we don't impose the error to go to 0. We only assume that it doesn't go to 1. This is the usual kind of definition of a strong converse. We just generalize it to probabilistic protocols. Okay, so having defined this, how do we usually study transformation rates? Well, usually what we do is we use entropies to constrain rates. So let us kind of look at how these things are defined. So divergences of relative entropies are a very commonly used concept, and the most kind of well-known relative entropy is the quantum relative entropy, or the omega Q relative entropy. And in settings such as transformations of quantum states in restricted settings, we often encounter the relative entropy of a given quantum resource. So here, essentially, what we have is some kind of set of states which has been singled out as the free states of the given kind of setting. And if we minimize this entropy over these free states, we get a monotone, a so-called Ries's monotone. And for example, the most commonly encountered example of this function is the relative entropy of entanglement. So we have minimized over all separable states. And the point of this kind of definition is that this is a monotone. So for all free operations of the given theory, or free channels of the given theory, this cannot increase. And this allows us to essentially apply it in kind of like constraining transformation rates. So kind of following this idea will be essentially the free operations that we consider in this work, which I haven't still defined, is now, this will be a definition, that essentially a free operation is any transformation which takes a free state to a free state, probabilistically. Here we don't assume this CPTP transformation. So essentially, this is a very kind of like a relaxed definition of the free operation, because, for example, for entanglement theory, this includes the well-known cases of like local operations and classical communication, but also larger sets of transformations. So essentially, we want to make as few assumptions as possible at this stage. But the crucial point is that under any such transformations, whenever they are quantum channels, then this function will be a monotone, and this relative entropy will be a monotone. Okay, so now if we want to apply this to constrain rates, asymptotic rates of transformations, we have to consider the so-called regularized relative entropy, which is defined essentially as the limit of rho tensor n, the entropy of rho tensor n as n goes to infinity. And then there's a very well-known result, which has appeared in many different papers. I believe this is the first one, but maybe not. Maybe it's probably people knew about this even earlier. Is the aspect that is the fact that every rate, deterministic transformation rate, is upper bounded by the ratio of the relative entropies. So essentially, this single function, this kind of we take this function, evaluate this at rho at omega, and we can immediately get a constraint on the kind of the best achievable rate in this setting. Now, of course, what we would like to do is to generalize this kind of approach to our probabilistic transformations that we consider in this framework. But the reason why we cannot apply this approach in the probabilistic setting is that the relative entropy is not a monotone anymore if we consider probabilistic maps. So essentially, now we are dealing with transformations that are no longer CPTP operations. And for such transformations, this is no longer monotone. So we need a different monotone. We need just to follow a similar kind of conceptual idea, we need a different monotone to apply the same, to get the same results. So to define such a monotone, we first look at the so-called max relative entropy, which is a very commonly encountered function. It is defined as the essentially the least coefficient such that the state sigma upper bounds the state rho in the positive semi-definite, with respect to the positive semi-definite cone. Now, this function is very commonly encountered in quantum information, but usually in one-shot settings. So it doesn't appear by itself usually in asymptotic kind of constraints, but rather in one-shot constraints. And but of course, we can define here the kind of in the same way, minimize the kind of like a Dmax or max relative entropy of the resource. And interestingly, kind of the fundamental connection between the max relative entropy and the quantum relative entropy, the omega relative entropy, is the fact that if you take the smooth regularized max relative entropy, so if you not only regularize it, so not only take n going tensor copies of rho going to infinity, but also smooth it in an epsilon ball around rho tensor n, then we actually get the quantum relative entropy in the limit. So this Dmax of a given resource, it converges to the quantum relative entropy of a given resource if we allow this smoothing and regularization. So there is a very fundamental connection between the two quantities. Now, okay, so having defined Dmax, now we will use Dmax to define a monotone, which finally will be able to constrain transformations also in our probabilistic setting. And that function we will be using is the projective relative entropy, or the Hilbert projective metric. And is defined as essentially the sum of Dmax of rho versus sigma and Dmax of sigma versus rho. So it's like a symmetrized version of Dmax. And well, this idea, of course, dates back to, well, Hilbert. But in quantum information, it was first applied by David Reeb and others in a paper that essentially dealt with transformations of quantum states, but hasn't looked at resource theoretic transformations like we do in this case. So indeed, we can define this kind of like a projective relative entropy of a resource. And the crucial aspect of this function is that this is a monotone for every probabilistic transformation. So it doesn't matter, the probability here doesn't matter. For every probabilistic operation, for every completely positive operation, even this essentially is a monotone. So it cannot increase. And yeah, of course, we can define the same kind of like a regularized variant of this quantity. But since this is based on Dmax, which is like a one-shot quantity that I mentioned, and the connection between Dmax and the relative entropy is with the smoothing. So we could ask, of course, what is the smooth regularized version of this projective relative entropy? And I want to stress that this is a priori, this is not immediate, not clear at all, because this function is very differently behaved from Dmax by itself, because this other term can be huge. And indeed, I mean, Dmax between two states, as you might remember from the previous slide, is only finite if the support of rho is included in support of sigma. So in this case here, this quantity will be only finite when rho and sigma have the same support. Okay, for every other case, this will actually diverge to infinity. And in general, this term can be huge, and this quantity can be very different from Dmax at the level of one-shot quantities. But our first result is actually that if you allow this smoothing and regularization, this converges also to the quantum relative entropy. So even though they are so differently behaved, the quantum relative entropy of Dmax versus the projective relative entropy, actually with this suitable smoothing, we get the same quantity asymptotically. And so how does this happen? The main proof idea will be to use the known result that Dmax by itself, it goes to the quantum relative entropy, the regularized quantum relative entropy asymptotically. And what we can do here is we can essentially choose this kind of optimal sequence of free states. So these are optimal states. These rho prime n are optimal states in the epsilon ball of rho, while these sigma n are optimal free states in the definition of Dmax. And essentially, okay, I want to stress Dmax and the projective relative entropy are very differently behaved. So we cannot just immediately take this sequence and apply it for the projective relative entropy. But what we can do is try to, well, identify the sequence and grab onto it and try to find a way to asymptotically go to the same thing. And that is what we will do. So we define a new kind of sequence of states, which are defined as follows. So we have this kind of definition, and this parameter eta is based on this epsilon. And epsilon, you might remember here, it goes to 0. So this quantity will actually be very large. And then, so this state omega n, these states omega n will actually be very close to rho prime n. And again, rho prime n is very close to rho tensor n. So what we get is that this omega n will essentially be very close to rho tensor n itself. And we can show that this asymptotically, it goes to relative entropy, the regularized relative entropy of the given resource. And by essentially, so this optimal sequence allows us to indeed reach the optimal value of quantum relative entropy asymptotically. Yeah, so that's the basic idea. Having kind of established this, now we can finally go back to our probabilistic rates and establish general restrictions on these asymptotic rates. So our our result on the converse bound is that every transformation rate in this probabilistic setting, so using any probabilistic protocols, is upper bounded by the ratio of the projective relative entropy regularized and the quantum relative entropy, the omega k relative entropy, also regularized. And just, I mean, to clarify the difference between this and the kind of the relative entropy bound, what we know is that in the deterministic setting, every rate is upper bounded by the ratio of the relative entropies. But what we have shown here is that in the probabilistic setting, a bound we can get actually only has the same denominator, but a different numerator. So, and this quantity can be very, very much larger than the relative entropy. So these bounds are very different from each other. The main idea again for the proof is to use our first result, which is the asymptotic equipartition property for the projective relative entropy, and then combine that with the monotonicity of this quantity for all probabilistic protocols, and then we play around with the errors a bit, and the result follows. Okay, so of course, this is a converse bound, but we haven't discussed how tight it is, and that's a fundamental question to answer. So to talk about achievability of this bound, let us first make an assumption or constrain ourselves to a specific type of quantum resources. These are so-called affine resource theories, and an affine resource theory is defined such that the set of free states contains all states in the affine hull of the set of free states. So essentially, there's some affine space, and in this affine space, all states are free. And this includes, for example, the resource theory of coherence, or thermodynamics, or asymmetry. And in every such resource theory, we get that the rate of transformations under these kind of the free transformations that we consider here is given exactly by the ratio of these entropies. So what this means is that there is no better bound possible. This bound is actually the tightest possible bound. Yeah, this exactly gives us the transformation rate in this probabilistic setting of our work. Now, the main idea for the proof is to use the fact that the existence of a transformation which maps two states, essentially, it can be reduced to just monotonicity of the single function, the single projective relative entropy. It characterizes this at the level of one-shot transformation. So essentially, we take this one-shot result and we turn this into an asymptotic sequence of protocols which achieve our desired transformation. But of course, not every resource theory of interest is affine. So what we would like to understand is other examples for which this is achievable. And one fundamental example for which we can show achievability is entanglement distillation. So in entanglement distillation, the target state, omega, is just the essentially the Bell pair, or the 2-qubit maximally entangled state. And here we can show that for every state, for every input state, the rate of distillation, or the rate of transforming rho into the Bell pair, is given by the regularized projective relative entropy with respect to a set of separable states. And one interesting aspect of this is that in the deterministic setting, we don't have such a formula. We don't have a formula that works for every input state rho. And here in the probabilistic setting, we were able to establish a general formula for the distillation rate of every input state. The idea will be similar as before. The fact that we don't have now if and only if conditions for the existence of transformations in the probabilistic setting, but what we can do is use a similar kind of condition, which is based now, it's no longer based on just the projective relative entropy. It uses a slightly different function. I don't want to go into details about this now, but if you are familiar with these research theoretic kind of definitions, this is essentially equivalent to the fact that the standard robustness of omega, or for this particular trace of omega, is equal to the generalized robustness of omega. And these are two different monotones for resources, and when they are equal, this allows for some simplifications. And in this case, we can show they are known to be equal for the maximally entangled state, which allows us to essentially get a nicer achievability bound. Now, to look more closely at what this entanglement distillation example shows us, let us look at the fundamentally important case of isotropic states. So isotropic states, okay, so we want to understand the rate of distillation from an isotropic state. And what we can show is that in our setting here, the probabilistic rate, this projective relative entropy will actually be additive for isotropic states. So we can compute exactly this asymptotic rate of transformation. And the regularized relative entropy, the standard kind of quantum relative entropy of isotropic states also is known. It is known to be given by this function, but we can show that, I mean, these functions are almost never equal except for trivial cases. So we have a strict inequality here, but we know that the regularized relative entropy upper bounds every deterministic rate. So we have a strict inequality between the probabilistic rates of our setting and the deterministic rates of, well, the conventional kind of transformations in Shannon theory. And if we plot this, actually, the gap can be quite significant. So here, if you look at the very bottom of this plot, we have the distillation rates plotted against the parameter P of the isotropic state. And if you look at here, the deterministically achievable rate all have to be rates, all have to be in this kind of regime here. But our projective relative entropy bound is given by this red line here. And this is the tightest, it's again, it's achievable bound. So it actually is possible to reach it. And so every protocol in this regime is achievable, but only in this probabilistic setting. So we should see that we can strictly go beyond kind of the usual Shannon theoretic regimes. Now, the case of distillation is particularly interesting because we can obtain some stronger bounds for distillation. And our final result will be about a kind of constraining distillation protocols. And in distillation protocols, essentially, what we now want to understand is error, the trade-offs between the errors of distillation, so the error in the kind of target state, how far it is from the desired state, some pure state psi, and the rate of the transformation. So we show a general kind of upper bound, or like, well, a trade-off essentially between the rate and the errors here. And so I don't want to kind of go too deep into this bound, but I want to give you two immediate consequences of this result. First is that our bound is actually a strong converse. So the bound based on the projective relative entropy is actually a strong converse bound for the case of distillation. So essentially, if you exceed this bound, the error has to go to this rate. If you exceed this rate, then the error has to go to 1. So essentially, every protocol is useless beyond this rate. And one other interesting consequence is that there is no super exponential error decay. So this allows us to look at how fast the error can go to 0. And it cannot go to 0 too quickly. Okay, so this formula, it forbids an error that goes to 0 super exponentially. I mean, okay, it forbids when this quantity doesn't, I mean, when this whole thing, it might trivialize, because there are cases, for example, for pure states, when this actually is infinite. So whenever this is not infinite, then we get a constraint, which is non-trivial, for example, for all full rank states. And it shows that there is no super exponential error decay even in this probabilistic setting of our work. Now, just want to clarify kind of here, because you might be familiar with rates that look like this, which are, for example, used very commonly in understanding entanglement transformations and, for example, connections with tensor ranks of pure states. And these transformations, they use, for example, LOCC transformations in entanglement theory, and they don't allow any error. Okay, so this transformation between two pure states, psi going to phi, is exact. So there is no error there. What we show is that this definition cannot be applied when this input state is not pure, or, well, when it's highly mixed, we cannot do this anymore, because there has to be an error, and this error cannot go to 0 too quickly. So we cannot just take, this is a 0 error definition, and there is essentially no possible way to define a 0 error rate for highly mixed states, even in this probabilistic setting. This is one consequence. Okay, so just to conclude, what we have established is general constraints on all possible probabilistic protocols. And I want to stress why this is non-trivial, because we have changed the definition of a rate. We have gone beyond conventional Shannon theory. So a priori, it's not clear if there should be any constraint. Maybe every rate becomes achievable. We don't know what happens in that regime, but we have shown that there are general constraints that every rate has to obey. And we have exactly characterized them using this projective relative entropy. Now, in many cases, we have shown that these are actually the best bounds possible. So they are achievable in many cases. And indeed, we have shown that they can be strictly larger than the kind of the well-known relative entropy bounds. So this approach goes strictly beyond Shannon theory. Okay, and one follow-up question which you might have immediately, and at least, well, we had, is, okay, so before the quantum relative entropy was known as the bound on transformation rates, it was known as the error exponent of asymmetric hypothesis testing. And this is often considered the kind of the fundamental operational interpretation of the quantum relative entropy. And one could, of course, ask, is something similar possible in the setting of our work? Is this projective relative entropy relevant in a similar way? And indeed, in a very recent work, essentially a follow-up work, we show that when one can define a task of hypothesis testing in which this projective relative entropy plays the same role as the quantum relative entropy. So these are really kind of like two fundamentally kind of similar quantities. One open question which we have not been able to show to prove is the kind of better bounds when peer-to-peer transformations are considered, for example, under LFCC operations, because as I mentioned, pure states are very differently behaved when we do these kind of probabilistic operations, and our bounds are not able to recover some of the results which are known for pure state transformations. But I don't want to make this seem like a limitation of our results, because I believe that the kind of the more noisy case is more useful in practical aspects. But conceptually, I think it's very interesting to understand exactly the relation between peer-to-peer transformations and mixed transformations, and we don't have an answer yet to that problem, so that's an open question. And with that, thank you very much for your attention.
Okay, thank you very much, Bartosz. So I'll open the floor for questions. I think Nilanja has a question.
Hi, Bartosz. Thanks for a very interesting talk. Something I don't personally know a lot about, just want to throw the question out there. People have studied SLOCC entanglement conversions, right? Stochastic LOCC. So does that fall in your framework? And if so, is the result for entanglement, distillable entanglement that you get, match what they would get for SLOCC?
Yeah, so I didn't want to go into kind of SLOCC because I wasn't sure if, this rate that I showed here at the bottom is essentially usually considered under SLOCC operations. This is essentially in this works of, for example, Matthias Christian looked into this kind of tensor ranks and kind of relations between SLOCC transformations. So this is exactly what I was talking about here. People have looked into SLOCC transformations, and SLOCC is a subset of the operation that we consider. So all of our bounds are also upper bounds on what you can do with SLOCC. But one could potentially hope to get better bounds for SLOCC under some constraints. So I think that our bounds will be generally very strong and probably tight-ish for highly mixed quantum states, for full rank quantum states. But for pure states, one could hope to obtain better ones, and that's what people have done previously, mostly focused on pure states with LOCC. So yeah, so to answer your question shortly, yes. I mean, our approach is more general, but for pure states, it's actually too general, maybe. So yes.
So is it known what the distillable entanglement is for mixed state under SLOCC? And if so, do you get an achievability with your result?
I don't think it's known exactly what it is, except for pure states. For pure states, given by there's the tensor rank again comes into play.
Yeah. Okay.
But for mixed states, I don't think there is anything known. And no, our results, our achievability results are strictly for non-entangling operations. So this is the only achievability results we get. So that's a larger set of operations than SLOCC, yeah.
Yeah, indeed. Thank you.
Are there any other questions? Maybe I have a quick one. Can you say a bit more about this post-selected hypothesis testing you mentioned at the very on the last slide?
Right. So post-select. So essentially, yes. So this is something that essentially we did as a way again to understand the meaning of this projective relative entropy. And so in conventional hypothesis testing, essentially we have a measurement which has two outcomes. We guess one state or the other, and then we understand the errors of this transformation. And in this post-selected hypothesis testing, what we do is we allow an additional outcome that is like an inconclusive outcome. And so if we get that outcome, we ignore this result, and we only look at what happens for the first two measurement outcomes. And so the post-selection happens because we have to essentially condition on the conclusive outcome. We have to disregard all inconclusive outcomes, and then if we condition on this conclusive outcome, so essentially we consider three outcome measurements, but we ignore all the third outcomes. Essentially, that's what happens. And in that setting, it is remarkable because essentially all the calculations which are known for channel theory, they simplify a lot. Everything becomes much easier. And for example, there are no second order terms, for example. All the second order theory that we've just heard about, it is completely irrelevant for this post-selected setting, because all the rates, they only depend on the first order terms, essentially. And in this setting, we get exactly as the kind of the exponent, as the error exponent, we get this projective relative entropy. So if you want to look at more detail, I mean, I don't have the formulas here because it's a different paper, but if you want to look into more detail, then we explain this in this recent archive preprint.
I see. Thanks a lot. So let's thank Bartosz again. And now I believe there's a group photos.